Hello everyone! Hi, welcome back to Live Coding with AWS. I'm Julio, happy to be here with you guys again. If this is your first time on the show, this Twitch series is where we are sharing directly with you guys and our space to interact and solve questions and do whatever you guys want to do. We are here to make sure developers have the tools and the knowledge they have to be successful with AWS. And much of that is around application architecture and making sure that your app is not only ready for the cloud, but well architected in a software architecture and software engineering sense in general. So towards that, we've built this AWS well-architectured framework, and this is what I've been talking about recently. And the AWS well-architected framework is built around these 5 pillars: the security, reliability, performance, cost optimization, and operational excellence. And we've been covering the questions from each pillar, and we are going to dive deep and code each one and really build something that is completely compliant with this, with all of those pillars. But there's a lot of design and thinking and considerations for this that it wouldn't be much of a help if we just shoot out some code to you and says that it runs, it is well architected without explaining. So this is what we are here for, really understanding what a well architectured application is and getting to code one together. So let me know anything that you guys want to build in this sense. I would be happy to talk about it here. And today we'll be focusing on the performance pillar, and there is a lot to that. So let's jump to the security, or to the performance pillar section and their questions. We did reliability last week, so now we'll address performance. And just like the other pillars in the well-architected, this one starts with these design principles, and just let's gloss over them and make sure we understand the basics of performance on AWS and the things that we have to keep in mind while implementing these solutions. So the first thing is to democratize advanced technologies, and this is not a sales pitch or anything. This is just meaning that in traditional IT, it's hard to optimize performance by adopting new technology. For example, when talking about databases, such as adopting Hadoop or Spark or a big data solution, this is something that many companies have on their repertoire easily, but for many others, this is very hard to get through the doors. You have to convince managers, you have to put hardware and software in place and do a lot of stuff. And AWS makes this much easier. You just spin up the service, provision, and go. So this is pretty much it. And the ability to go global in minutes, we'll see that performance is very related to location. Using serverless might help. We're going to see how, and if you can reduce your load on servers. This is probably interesting in many senses, including performance. And all in all, it allows you to test and experiment more often and launch more environments and do what you have to do to make sure performance is just right for your app. The last one is mechanical sympathy, just using the trade-offs that make sense for your environment. So that's it. And after those principles, it goes directly to the questions. And it starts with this selection theme. And we are going to speak a little about this because much of the performance benefits that you can do is just by selecting the right software and the right services for you. And it's sometimes not so easy, you know, and we hear that a lot from customers. If we go to the AWS products page on /products on the main site, you'll see that we have several compute services, several storage services, and it's nearly 100 services. And how do you choose among all those things? It's something that we hear a lot, and we're going to cover a bit about this today, because that's where it starts. And the first question is, how are you selecting the best performing architecture? And to make it easier to share some thoughts and to record what we're doing here, I put together some notes in a gist, and I'm sharing this in the Twitch chat right now. So this is the gist that we are running today. Hey Gina, nice to see you and everyone here. Let me know if the audio is not right, if the video, if you can't see what I'm casting at all, or have any issue, just ping me here and we can try to make things a bit better. So in this theme of how do you select the best performing architecture, the most important thing is what Edward Deming told us. William said, "In God we trust, all others bring data." So let's try to remove the guesswork and imprecise information as much as we can, and work more strict, as more closer to engineering, and let's translate this into more precise terms. So performance is a very general and subjective term, right? It's a feeling, not data. So it's better to think of performance in specific terms. For example, latency. Latency is much better. You can measure latency in milliseconds or in any unit of time. It's the responsiveness or the liveliness of the system, or how long it takes for the request to come back. So, and latency is always a trade-off with throughput, meaning the amount of data that you can get per second or per unit of time, or how many transactions per second is your system able to achieve. And we're going to see that those will be always in conflict with each other. You have to think if you're building for latency, if you're building for throughput, or perhaps find somewhere in the middle where the solution is just right. And more than that, this is not something that's steady over time. It's sometimes proportional to other quantities. For example, latency is usually related to the concurrent users, because if you have, for example, many concurrent users, you may have more threads than your application server is, or many more connections that your application server is capable of handling, and this may increase latency, so you may check this out. Or according to your dataset size, for example, everything works fine when you have hundreds of rows in your database, but when you get to millions or billions, your throughput's probably gonna be different, and perhaps your latency as well. So translating this into actual measurements is really important, and this is part of eliminating all the guessing. But it's not that simple. You have to get some exploration, and we are going to do this today and see how performance looks like, and trying to get a sense of the performance percentiles, because the average doesn't always means a lot. Sometimes your average performance is good, but when you look at the 99 percentile, you're going to see some things that you might not like. So we should be a bit deeper on this in a few minutes. There is flaming graphs and a lot of work done by Brennan Gregg from Netflix. If you don't know who I'm talking about, I believe it's Brennan Gregg, like this. I hope I'm on the right person, and you should check his work on systems performance. all that. There are lots of talks, and for those wanting to dive deep on performance, I highly recommend you check his work, especially on flame graphs and things like this. He's done many interesting tools and publications. And decision makers, is the sound bad? What do you mean bad? Like noise or not loud enough, Felicimo? I will increase the audio a bit, make it, give it a little more gain here, and hope we are better. I hope this sounds better. I will try to speak more loudly and clear just to make sure it is okay. It's a pinch better, a pinch higher. I hope this is much better now. Let me know if you have any more issues. Thank you, Franz. Thank you, Felicissimo. I hope this is just right for everyone. It's a bit hard depending on your setup, but let me know. And the most important tool for making these decisions are going to be these decision matrices like this. I don't know, everybody uses a different thing for this, and this is how I justify decisions in most projects. And back in the time when I did consulting, I used to feel a lot of those. So just pick your results from your explorations. So for example, if you found those great databases on the web and you were unsure how you compare them, just establish as clear criteria as you can. This is not so good. Let's try to make this a bit better. So for example, when we talk about latency, instead of just assigning a score, you can do a bit better and specify, for example, that the target is 0.5 seconds as a reference or something like this. You should, well, add a column, do a bit better. The idea is the more precise and the more info and the more you can build on your matrix, the clearer it will be and the easier it will be to explain when someone arises and says, hey, why did you pick this database instead of this other? And if your project is interesting enough, this will happen a lot. So it's always good to say, instead of, well, I don't know, I just was wanting to learn it or found it, my friends are using and I want to be with the cool kids. It is better to have a decision matrix or something similar, just to say, hey, you know, we had this requirement of latency and this database did better than that, but we really value documentation and support, so this waited on us to choose and ended up choosing for this DB or this other DB. Okay, so all right, this is how you usually select technology. And let's dive a little bit deeper on this. I'd like to talk a bit more about testing and making some exploration and understanding latency and throughput of the system. So let's build a simple app on Elastic Beanstalk for a start. So we're going to use many services today. I will try Elastic Beanstalk. Let's create a new app. It seems we have one from last week here. Let's see if it's up. If it is, we can probably use this. So let me see. Yay, it's up. So we already have an app up, and we can see here in the monitoring section, or in the health section, sorry, we have some monitoring data, not so much. I hope we have more here and in a bit. And the section that I want to pay attention is this latency and load averages on the system, and especially these latency percentiles. If we're gonna dive deeper on this when we talk about measurements and active monitoring and passive monitoring, but from here we will understand how our latency distribution is. So we're going to see how much takes the 10% of our requests are below this number, 50% are below this one, until we see that 99% of our requests are below a given latency score, and the load in 1 minute, the load in 5 minutes. Let's try to get some data in here. And this is the thing to talk about monitoring. We're going to talk about how to generate load and understand this a bit better. But it is great if you have CloudWatch like we're having here in Beanstalk, or other service such as other monitoring services such as New Relic or Datadog. They will all, or they should provide you this kind of information. It doesn't matter really much the tool. I'm just showing the kind of information that you need in order to build a matrix, a good matrix, not this crappy one that I have here, but you should feel the more precise information you have, the better. And something that is not always easy to do is measure like the quality of documentation or the community strength, but you should get at least a star rating for this, like 1 to 5. I tend to normalize from 1 to 5 on everything, just because multiplication and sums gets easier and to interpret and to calculate. So there's people who do 0 to 1 or 0 to 100. It kind of depends, but I like going from 1 to 5, makes it quick and simple. So this will change, of course, from the complexity of your environment. From simple projects, this may be enough. For more complex, you may build a spreadsheet application that takes a lot more into account, but you get the idea. This should, as long as you have an answer and it's not guessing, it should be fine, right? And then let's dive into selection in specific terms. So how do you select your compute solution? And here is a tricky one, because we have 3 types of compute solutions on AWS. We have serverless compute, we have containers compute, and instances compute. So let's give a little bit more of a perspective onto this. We've covered a lot of serverless before, and serverless is all around Lambda. So let's take a quick look on Lambda. The idea of Lambda is that instead of having your code deployed and into servers that you manage and you control, you just give AWS a function. Here we can see the code of one of Lambda function that I have, and it can be in several languages, in Python, in JavaScript, in Java, in C# and whatnot. And once stored, this function is going to react to several triggers and events. Here it's responding to CloudWatch events, but we could bind this trigger to APIs or to devices or to skills or anything like this. And the great thing about Lambda functions is they charge by the only when they're actually being executed. So the exact price is a fraction of a cent per gigabyte second. So here in Lambda, we can just to make sure that I don't speak the wrong number. It is 0.00001667 per gigabyte second, being so that if we change the configuration of our function to have half a gig and run at most for 2 seconds, the most it will 2 minutes, the most it will cost is, if it uses all those 2 minutes, it's going to be 120 seconds times half a gig, so it's 60 seconds times this cost. So this is a pretty strong reason in costs to use Lambda. and serverless in general. And an important detail when it comes to performance is that there's small lines here. Your function is allocated CPU proportional to the memory configured. So if you are running on serverless, you will see that the CPU changes when you change this value. So you probably want to provision different copies, or in your load testing, test different values of memory and see how your function behaves, because this can really help to optimize for the ideal performance that you're looking for. All in all, I would say go to the lowest memory that fits your needs, but make sure you test appropriately. And on another thing that's influential is understanding container reuse. So there's this article, Understanding Container Reuse in AWS Lambda, where Tim Wagner shows the cases in which the containers go up and down as Lambda functions are executed. And the idea is you have to think that when your Lambda function is idle, it's not being called a lot, it's no traffic, perhaps it's during the night or things like this, you don't need to, your container may go down. So what will happen is during those times when you look at your percentiles distribution, you see that most of your requests are okay. Perhaps 99% of your requests are below a certain number, but on the high range you see spikes in latency because perhaps 1% of your requests are getting the cold container and you have to boot the container in the application. So you want to make sure that when you're deploying Lambda functions, your startup time is really small. So and this is pretty different between the age of serverful. When you boot your Java application server and this is going to stay on forever, and you start this gigantic connection pool and things like this doesn't make much sense with transient compute solutions like Lambda. But we do have limits, right? For example, here you can't go above a gig and a half of memory, and I believe you cannot go above 5 minutes, if I'm correct. So if your computation is long running and requires a lot of memory, for example, in compute and things like this, and hey, I'm glad. I wouldn't say that Java lambdas are very slow because of JVM. JVM certainly adds to the startup time, but we take that into consideration in the container config, so it doesn't go down so often, and your code also plays a lot in that. So Java code is usually structured for application servers, and that's not probably going to live well on Lambda, so you have to think a bit about your code, your pool size and things like this, your CRUD configuration. But all in all, Java is great, but it certainly have its issues like any other language. It's a matter of trade-offs, but I'm glad that all of them are supported. I'm an old Java bigot, but I've been doing my JavaScript as well, so it runs. See, and we're gonna see how that more of that in a second. But yes, just those things. Make sure that you test for different memory and capacities, memory and timeouts. Make sure that you understand container reuse and make your load testing to see that your application is startup time is right and things like this. So this is pretty much it for performance tips for Lambda, and we can dive a bit deeper on this if you guys would like, but there's not so much to it because after all, in the end, Lambda manages the underlying containers for you, so you don't have to think about how are those tasks being distributed, how are the events getting there, how is the code deployed. It's all right there and good to go. So another option is when you don't have the same properties, the same when you run outside. For example, if you want other languages, so Lambda supports C#, Java, Node, Python, but what if you want Go or Ruby or other languages? Well, there are things you can do. For example, the Apex framework can run Go. You can run other languages on Java, for example, Scala or Groovy or JRuby or things like this. You could run other languages on C# environments such as F# and things like this. But it gets to a point where you better run the thing yourself and execute everything locally. And one other very important part is that you're not going to be able to replicate exactly Lambda in your own infrastructure. So there is a SAM local for testing and development, but if you want the exact same runtime as you have in production, you may want to use containers. So we are pretty heavily invested on containers, and as that is a major trend, and if you'd like to use containers and manage containers directly, this is certainly interesting. Here you can see that we are continuously launching new features on containers. We recently added ECS capacity. ECS is our container service for EC2, and now it can add and remove Linux capabilities directly to containers and allow for direct access to privileged instructions and things like this, and syscalls, and can make your containers not only run faster but get any kind of capability. So this is we're bringing new things every day, and there's a lot of extension points on ECS and a lot you guys can do. If you want to know more about ECS, I highly recommend you see Abby's series here on Twitch. Abby's been talking a lot about containers, and we have videos of all of that, from nothing at all to containers scaling on the cloud. So check this out if you guys want to know more about containers. And we can probably run just for a more concrete example, let's pick a Docker container for, I believe there's one for that game 2048, the Docker version, and this should be pretty easy to build. So let me try to get this Docker file. So I just want the Docker file. Let me get the raw one from here. So this should be enough. Let's see if Beanstalk can run that directly. So I'll go to Elastic Beanstalk, create a new app. Let's say it's 1248, and again, this is probably alright for web environment. I will pick Docker as an engine. We can do load balancing and auto scaling or a single instance to make it go a bit faster. Upload my own Docker file. Let's see if this works, and upload the version. It's this environment, just go and run. If it was a bit more involved application, we could add database, add resources, add whatever. I'm just going with the full settings here, and let's see if it's enough to run. And behind the scenes, Beanstalk is going to manage the deployments and the execution of the container. So I'm just highlighting that you have two different options here. If you don't, if you're not familiar with container management and container placement and container networking and things like this, and you don't want to know, you can just ship your Docker file to Beanstalk and let it run your thing, or you can go to ECS, the EC2 Container Service, and here you deploy, create your cluster, add your Docker file, manage your hosts, see your running tags, and all of that. So just two ways to go about containers, and again, use the one that makes more sense for your application environment. Again, this always gets us back to the decision matrix. So should I use ECS or Beanstalk to my environment? Which one is better? I don't know. Pick your weights, define your criteria, and see how it goes. That's what I would advise most people, right? Because each environment is kind of different. But that being said, when it's all containers or serverless or Lambda functions, at the end of the day, it runs on hardware, right? And let's talk about instances then. Instances should be seen as the bottommost like horsepower of compute. So those will be the basic elements that are going to define the performance of your app. So it's very important for performance efficiency that you understand what instances are, how they behave in every minor detail. So I will run the risk to be overly detailed in my explanation now about instances, but I really want everybody to get this right and understand what instances are. So when you fire a EC2 instance, when it boots, you have this, you're actually renting from AWS, if you will, a couple different things. So sorry about the clicking. You are hiring CPU, memory, perhaps some disks, perhaps GPUs, perhaps FPGAs, and one or more network interfaces. So let's see how it all happens in EC2 while Beanstalk goes on with launching our Docker environment. I hope that if that Docker file is good, we should be running in a couple moments. But meanwhile, let's keep talking about EC2. So here in EC2, let me get a different region for us. I've got a couple machines running over there, and launch a new instance. So when you run the new instance wizard, there's a couple of small letters that not everybody see here, but those are pretty important. And they say about the root device type and the virtualization type. So the first thing is root device type, and you have two options here. You have some volumes that are EBS on the root and some others that are based on instance store. So instance store is another kind of storage that we have, and the main difference is that EBS is persistent and instance store goes down and disappears when the EC2 instance is stopped and started. So we also say instance store is ephemeral in that sense, that once your instance is stopped and started, this data goes away. And the other thing is this virtualization type. This one is HVM, and this means it's hardware assisted virtualization. So when you make a network system call to send data through a socket, for example, the hardware can know and safely and in a very performant way help to deliver this packet to this machine, for example. When you have virtualization, other virtualization types, we have paravirtual in some cases, and those will be like emulators, when there is a piece of software, a driver in the operating system that translates virtual machine calls to hardware calls, and this have some disadvantages and advantages, but all in all, for new instance types and new applications, I advise everybody to use HVM. So this would be, always make sure that you're using the HVM virtualization type for the latest features in EC2. So there's a bit of a background noise here, that's true, sorry about that. I will try to tilt the mic my way and see if the noise gets a bit better. I hope this is better. Thank you, GB411. This is really helpful. And I see the discussion about Java on Lambda, and it's really this old is Java is slow or not talk. I wrote pretty performant Java code on Lambda, but it's surely different from writing code to an application server that's going to be up forever. So this really mind that. So let's understand exactly how the Linux instances works, and especially because we have a bit more options on that. But all in all, the important part is selecting a family and the instance resources that make sense for your case. So first, CPUs. All instances, when they say like an M4 that has 2 vCPUs, those are dedicated to your virtual machine, and you are going to own those CPUs 100% as long as your VM is running, except for T2 family. T2 is burstable. So T2 micro is not actually one CPU, it's like 10% of a CPU. It's small, you have those on the documentation, those rates, but the thing is they speed up as you don't use the capacity that you provisioned, and when up to a certain time they burst and then they fall back to the baseline performance. So this is only for the T2. All other instance types, one CPU is one CPU. But on CPU performance, you have to understand that those are not equal, right? For example, M4 larges have 2 vCPUs, and C4 larges also have 2 vCPUs. So what is the difference? What is the performance? How performance is different between M4 large and C4 large? Well, this is another detail hidden in the UI. If you see here up in this description, the M4 large can provide you 6.5 ECUs, Elastic Compute Units, an abstract unit defined by Amazon, so you can compare instance types. They have a better definition. They're like 1.0 gigahertz of processor from I don't know when, but the idea is that it's not important. The important thing is that this one should offer 6.5 ECUs, and this one here is 8 ECUs. So C4s are targeted, as the name implies, at compute optimized. So those are faster CPUs for compute, and they can achieve a bit higher processing, but because they are this generation. But if you see on the memory side, this M4 large has 8 gigs of memory and the C4 has 3.75. So if your app is more CPU intensive, you may be better off with a C4. Or if you're memory intensive, you can pick R4s that they have the same 2 CPUs. Those CPUs will get you a bit better than M4s, but not as much as C4 performance. But you have 15 gigs instead of 3.75. So for memory intensive apps, this is important. And you get the picture. And for CPU and memory, that's all. We go up to the very new X1 32 extra large with 2 terabytes of memory here. So we have 1 terabyte, 2 terabytes, 4 terabytes of memory and we announced, I guess, up to 16 to be coming soon, and we should be having that. And this is a bit different according to your region. So not all instance types are available in all regions, but if they are, please check that you have the instance size that is appropriate to your app. And this is another thing that Beanstalk helps. So here in the configuration of your Beanstalk app, on the instance type, you can either change the instance type anytime and it will apply this automatically, or you can clone this environment using a different instance type. So this should be clone and change its configuration, or you can save the configuration for later, so it's config A and do blue green or A/B testing and see how different configurations behave. So this is pretty a helpful feature of Beanstalk, this change of instance types, because this is major in finding out what performs better. And the next thing I would like to talk about is EBS and instance storage. This is the second column here. And you will see that in new instances and compute instances, EBS is usually the case, and you don't even have instance store in many instance types, but in some cases we have. And when you see here, for example, that the R3 X large has one disk of 80 gigs SSD, or this R3 8X large has 2 disks of 320 gigs SSD. This means that inside the same physical host, you will see the connection. You will see these devices. So EBS is a remote service, and SSD is an instance store is a local service, is a local device. So this is over the network, this is over the local bus. So this has tremendous implications in latency and throughput. But this will be the capacity of those disks is predetermined. Here in this instance type, there are 2 disks of 320 SSD, and this is it. You can't have more, you can't have less. This is what it offers. Here on EBS, you can dial up and down as you please. You can have more gigs, less gigs, different performance characteristics that we're going to see in a minute. So this is pretty important. Let's go on. So for the first thing I told you guys about EBS and instance storage that we must never forget is that instance storage, when you stop and start, this data is gone. EBS, when you stop and start, the data remains there. So this is, I had this in a small table here just for reference. The instance storage is ephemeral, EBS is durable. Instance storage is a local device, EBS is a network service. Capacity is predetermined by instance type on instance store, and in EBS you provision as you please. And the cost in instance storage, it is included in the instance cost, and EBS you have to pay extra. So if you stop and start EC2 instance store is gone and you don't pay for it because you pay for only what you use on AWS, but EBS you pay for what you provisioned and is stored there forever until you delete the volume or the instance. So I hope this makes sense. So next we have the other resource type is EBS optimized. So here I told you guys that the we have one or perhaps more than one network interface. And when you select an EBS optimized instance, such as, for example, let's go on with R3 for X large, because it has one drive SSD and it is EBS optimized. So the idea here is that you have one network interface towards EBS and one network interface towards your app. So if you have, for example, a database server running on here, you have a separate dedicated interface towards EBS if you set this as EBS optimized, and so it will not conflict. There will be no network contention between your storage network and your application network with your requests, responses, database queries, and so on. And after that, there is your performance on the network, how much you provision, and the yes. Here the last yes is if this supports IPv6. So I hope this is clear for everyone, but let me show you guys something a bit interesting. So here I would like to ask you guys, what is it worth this instance storage disks? Like, if this disk that just sits there and disappears when you stop and start, why the heck is that useful to anybody, right? This is an interesting question, and the first thing that always comes to mind is cache, like your Apache cache or virtual memory swap and things like this, or temporary files, logs, something like this. But because logs usually ship out of the server anyway, so they may live here for a while. And this is all good and valid, but it's a bit further than that. If you check the store volumes here, you're gonna see some instance types that are quite peculiar. For example, this D2 8x large instance type, it has 24 disks of 2 terabytes each. So why would someone want 48 terabytes in ephemeral memory, right? Why does this make sense? So the idea here is if you have replication, such as a file system replication, such as GlusterFS or Red Hat Storage and things like this, or database replication, such as Hadoop or Cassandra. If you have data more than once, right, replicated in 3 or many nodes, if ones fall down and take its data with it, it's not a big deal. Someone else is going to pick up the replication and copy the data again so that you're safe. So for those kinds of apps, it may be much more efficient to have 48 terabytes of local storage included in the instance cost, instead of having to go through the trouble of provisioning this amount in EBS and adjusting performance and paying more and things like this. So this may make sense. And another thing is, remember that EBS costs extra. If your web servers, for example, they just go up and down as requests and demand increases and decreases, you may not need permanent storage. Let's say you store everything on the database anyway, or somewhere else that's not on the app server, and you may not even need EBS. So in those cases, you may pick instance store root volume and just go with ephemeral instances, for example, and save a couple bucks, right? I hope this makes sense. Next is configuration details, and performance-wise, these things that are important here are detailed monitoring. This would give you 1 minute metrics instead of the default 5 minute metrics, and here is that EBS optimized instance, and additional charges may apply because it's a separate network interface, but yeah, you got it. This may solve lots of issues in network contention, especially when we are talking databases or file systems. This is pretty much important in those cases. And around tenancy, it is a bit debatable how much that influences on performance, because if you're in a shared environment, your neighbors may be busy and you may see fluctuation in your net CPU throughput, especially in T2 micros and smaller instance types. But you can have a dedicated host, so you make sure that you know where your instance is running. If you select dedicated, this means that you're not sharing hardware. All applications, all VMs that are running on the same hardware are yours, but you can't say what runs where. This is a software guarantee. A more strict guarantee is dedicated hosts, where you can launch instances selecting in which host it lives exactly. And this may be important for both performance and compliance reasons, so you can have if you have to license software per host and things like this, this may be easier to run in this way. So this is how instance store works. And next, storage, and here's where EBS performance comes to the table. Here we can see that the default setting is the general purpose disk, and the general purpose disks are very, very simple. They have 3 I/O operations per second. So if I have 200 gigs in my root volume, I will have a baseline of 600 operations per second. Those are 264 bits per operation, so this will give you it will give us this much throughput. And the idea here is that if you use less than this 600 IOPS, for example, your app uses usually 400 to 500, the extra you accumulate in a bucket, and you can spend this bucket to burst up to 3000 IOPS. So this is interesting. So let's think here. One thing that makes sense is asking, what about arrays? Should I do RAID arrays using these volumes? Does it make sense? What performs better? One volume of, let's say, 1 terabyte like this, or should I use 2 volumes of 500 and use striping to write simultaneously to those disks and have the load balanced between the writes and reads balanced across those disks? Well, I hope you guys can see that it is actually better to have 2 volumes in this case, because here they can burst up to 3000 each, so your combined burst could be up to 6000 IOPS, while if you had only 1 volume of 1 terabyte, you are already at your max baseline. So I hope this makes sense, and it's pretty important then to understand how bursting goes, and it's not hard, it's that simple. 3 IOPS per gig, burstable up to 3000 per volume, so it may make sense in some cases to have striping and arrays and do things like this and have them separate. Okay, and when you add volumes, you can add different kinds of volumes to those instances. So we can have volumes that you provision how much I/O do you want. So you can have here I provision the 500, but this says nothing about the IOPS. I can have I could put the default or even higher. For example, if I want 2000 operation IOs per second, I could use I could configure my disks like so, but you have to check that in EBS performance, in the EBS pricing, those volume types will have different costs. So GP2 is quite simple. It's 10 cents per gig per month, and that's it. On provisioned IOPS, you pay separately per provision size and provision throughput. So make sure you do the math on this. And next, we can add code storage and throughput optimized, magnetic. I'm not going to dive deeper on this. This is if you need other kinds of hard disks. Those are both SSD, but there are still use cases for hard drives, magnetic hard drives, for code storage, archiving lots of data cheaply, or if you're going to make serial reads through huge collections and you're just worried about the throughput, as is usually the case on Hadoop and things like this. And magnetic, if you only need a small volume with predictable, more cheaper IOPS for small volumes, this would be the common case for magnetic. And another volume that you can add here is the ephemeral volume. So here, all of those are on EBS, but if you remember, this instance type has got one instance store volume and you can change nothing about it. It's that volume of, if we choose the instance type, we've selected that. Where is that instance type that we selected? Here, the R3 4x large. It's got one disk, 300 gigs, and that's it. That's all we have on storage. Tags for manageability, let's add at least the name and Twitch storage performance. The security group, I will just launch this as it is. Create a new key pair, test key pair, something like this, just so we can boot this if we want to dive a bit further. But the idea is, you'll see that from the instance perspective, once they're bound, those are all disks and block devices, and you will see them in your instance, and they will have the performance as we specified. Okay. So yeah, talking about the container cold start, this is dependent per environment, as we were talking, and the size of your app is one thing, because this will be downloaded from S3 when your app boots. So beware that you don't want like gigabytes of deployment packages. It's better if you can deploy not that one big fat huge jar, but smaller jars per functions or per modules. That should help a lot with improving the container boot for Java applications in particular, but this is valid for other runtimes as well. And that's it for EC2 performance. And a couple of other details here are for special instance types. We have most instances and most apps will be fine with this, but in some cases, excuse me, you need a bit of more features. For example, GPU is important not only for graphics and gaming, But for machine learning, neural networks, HPC, everybody that's on high performance may want to use GPUs. And we have instances in the G3 and P2 families that comes bundled with, for example, 16 or many GPUs. So, for example, there's a nice post in the Netflix blog about GPU and neural networks. So Netflix is one customer that leverages this GPU with to make machine learning and run their models on GPUs and get incredible performance gains from this. I will leave it the reference for of you guys who would like to know more. Check this and many other cases around GPUs. So the thing is, we got GPUs, not only those that are fixed, but we just announced something called elastic GPUs. So if you're running on other instance types such as we are, you can add a GPU at any time. It's network-based GPU, so it's like AWS volumes, but for GPUs. Just plug in the GPUs that you need while you need them, and just compute on GPUs. And when you don't need it anymore, you can remove the GPUs and pay less. So this may be important for simulations and many other kind of scientific computes, and you don't need to change instance types to have GPUs. That's the idea. And another very special component is FPGAs. So we have this F1 instances, not here but on Virginia. I will show you guys some details around this F1 instances. So those instances have a special hardware component called FPGAs, field programmable gate arrays, that what they are basically an accelerator for any kind of workload. So they are very capable FPGAs. They are like huge FPGAs by any standard. And what it does is you write your hardware in your hardware development kit, deploy it, and your FPGA will configure its logic mapping so that it will run that code as if it was a native circuit built for that. So it's programmable hardware. And this is important for both reasons. You can be on the side of the persons who know hardware development and want to share that with the world through the marketplace. So you just publish your AMI with F1 support and go, or you consume this from other people that published FPGA solutions from the marketplace. So this is another component that may be important for your workload, especially if you're doing video transcoding and things like this. This is how it runs. So this is huge for many types of workloads. I highly encourage everyone to take a look at FPGAs. Pretty hot these days. But again, this requires some understanding of hardware design and how these components work. So just to make sure that everyone understands how CPU, memory, disks, GPU, FPGAs, and networking works for EC2 instances. And here's the blog and how you choose between them. So another thing that may be interesting for everyone is the other than the huge array of instance types that we offer, is the Intel features that we have. So AVX or single root I/O virtualization and everything that Intel has of features, we usually launch them within new instance types. We'll soon have C5s with Skylake processors and elastic network interfaces and whatever. If you're into the CPU details, I'll not bother everyone with the difference between Broadwell and Skylake, but this is much worth checking it out for the bottommost layers of performance. So we've already talked about storage, and this is what we've done for block storage. I would just like to highlight that we also have file systems and object storage. And the idea here is that you can build your own file system on EC2 if you, for example, if you want a global net distributed file system such as GlusterFS or Hadoop, you can just spin that. But we do have a service for that. It's AFS. So if you just want a shared file system that performs reasonably and works well, and it already have many of the NFS problems figured out, so just go for Elastic File System. But one thing that you have to be aware is pricing, because it's very convenient to have a shared file system, but it does cost 30 cents per gig per month. While if we check AWS S3, the pricing is dramatically lower. So in S3, that's object storage, where you just store the whole file. You just send it's just like this huge key value store. So the basic difference between one and another is that this one is a tree, this one is a hash map. So Elastic File System will be hierarchical file system with directories and permissions, NFS, mountable over the network and things like this. S3 is going to be an API over HTTP that you can ship your object for a given key, and it will store that and return that over the HTTP. So it's a very different thing, and it scales much better, right? As you be probably aware, hash map scales better than a tree, right? When you have a hash map, you can just grow and add nodes and have linear time operations or constant time operations most of the times. And with trees is a different thing. A directory you can't. They get slower as they scale. There's a lot of AFS to help that, but they are still a bit harder, and that's why they're more expensive. If you see, they are more than 10 times more expensive than S3. Okay, so S3 goes on standard storage and for 22 cents. 0.3 on infrequent access for backups and on Glacier storage. And they have different performance characteristics. For high performance, I highly recommend people choose standard storage, because the others will have different characteristics of accessibility. Okay, and that's it for the storage options that we have. So this is storage selection. And understanding the different characteristics between block storage, file system storage on EFS, and object storage on S3, right? So make sure that you understand those differences. Okay, block storage, file system, and object will behave completely different, and this is the whole theme of mechanical sympathy with your app. Further down, let's go to databases and how do you select your database solution. And this is pretty much all around CAP theorem. And if you don't know CAP, I will provide a bit of initial introduction, but the whole idea in selecting databases is understanding this. So let me show you guys what I mean by CAP. Every time that we need to store data in any distributed system at all, we are faced with a very hard choice, and this is how it goes. I will Let's say that we have a very small database that only stores one line, one record, and I will insert A, and it will store the value A, right? So that it will keep the value there, the insert command ran, it's stored, and someone queries, it will answer A. So this is pretty much how a database works, right? And the problem here with this setup, we saw in the reliability part that we always need redundancy. If this node crashes, this will have a problem of availability. So we need to change this to a network where we have two servers for redundancy, and when someone puts B, for example, and this gets to B and it's replicated here, so here is B and B comes out when someone asks, right? And if this server dies, I can still answer B because I still have one server up, right? I hope this makes sense for everyone. The problem is when this network is down. So right now, when you have this, when someone updates this to C, the network is down, so this guy still gets B, and what should we answer here? We can either answer C and be consistent and be available and have available okay, but consistency not so much, right? So this will not be a consistent answer. Or we can say, well, our network is down, so we don't know in what state we are, so I can't answer anything. So I would be consistent. I would not give bad answers or inconsistent answers, but this will not be available. So the idea here is to make it clear that there is no way around this issue, that when you have a network partition, this is a fancy name for this. When you are partitioned, you have to choose between availability and consistency. And modern databases changes this a bit by adding more nodes. So right now, most databases work in a distributed fashion. So if we are doing just add more computers. So for example, here we can add 2 more nodes. Say now we have a cluster, a larger cluster, and this is very interesting for both performance and availability and capacity, because right now we can, for example, say that this is D, and even if we have a partition here, it will update and update until finally you get the D there, but it might take a while. So this is what we say, this is eventually consistent, because it may not be consistent for everybody at the same time. So this guy may read B while this guy reads D, but in a while, when it gets there, it will be eventually consistent. So this is how it works. I hope that's pretty much simple for everyone, just making sure that everybody understands the whole idea behind the CAP theorem, and this is what drives our selection of databases. If we go here on the database solutions panel on EC2, on AWS, here are the options that we have. So we have RDS, DynamoDB, Elasticcache, and Redshift. So Redshift is for data warehousing. It's for extracting bulk amount of data with the best throughput, but not necessarily the greatest latency. So here it will run a massively parallel system, and it will be SQL, but it's more targeted at data warehouses and business intelligence. On Elastic Cache, it will run the distributed caches, in-memory caches, Memcached or Redis, whatever you prefer. Let's focus on RDS and DynamoDB because those are the more important in this performance and availability and cap. When we are on RDS, on relational databases, every instance we launch is going to be a relational database with highly consistent or atomic consistent features. So when we launch a new instance, you get to select your database engine type, and performance is a lot determined by your selection here. So you can run on the default flavor of MySQL, the regular MySQL or MariaDB that you can download and run on your computer. Or there is a special database here, Amazon Aurora, that's compatible with MySQL, but behind the scenes it's Amazon engineered database for Amazon infrastructure, so it performs much better than the generic MySQL. It's up to 5 times the throughput of MySQL, less lag in replicas, and many much more security optimization that you would see anywhere else. And this is for open source databases. If you prefer, you can run on Postgres. If your software is probably already designed for one of those, or even our Oracle and SQL Server if you prefer that. I hope it's not the case. I myself prefer the open source world, but it's all available here. And as I said, each one will be different for each case. And another option, but again here, what are the implications here on consistency? This will be atomically consistent, highly available, but it may not have the same latency as you would see on NoSQL databases. For example, on DynamoDB, it's a database, a NoSQL database by Amazon that stores everything on SSD and super fast instances and networks and really optimize it for this use case. And the good thing here is you can just say your table name, for example, events and ID as a key, and this will be again the same idea, the same relationships, a different data structure here. DynamoDB will use sharding and store your data in many nodes to make sure you have the read capacity and the write capacity that you need. So you can either use the default settings or pick your own read capacity and write capacity. This is defining how many reads and how many writes you can do per second, and you can change that on table creation or anytime at all, and it will even always scale by default to match what you provision here. So you can say that I want 10, start with 10 read capacities, 20 write capacities, and DynamoDB will provision as many nodes as it requires to keep this throughput. And one idea here that's very important and is that this is on average. So you're not going to get 10 read units or 20 read write units for every shard on your every partition, but overall the expected throughput of the whole system is this. And as long as you don't have one key that's much hotter than the others, this should be fine. And we're gonna see some workarounds for when you do have those hot keys and hot things. And for example, one use or one product that's much bigger than much more and requires much more throughput. So here you can set the auto scaling for your table, when it dials up, when it dials down on capacity, and this is it. Just what you need to create. I already have this policy name, so let's new role for Dynamo, and we're done. Okay. And one thing that's important here to work around that case, when you don't have, you have your throughput is fine on average, but you have one record or one item that's too hot, that's being accessed a lot and causing you issues. We usually do caching for this. And you can use, of course, Memcache or Redis on Elasticache. But now Amazon has its own DynamoDB cache embedded in DynamoDB. So DAX, DAX, is your embedded cache. Sorry for the Spanish here, it picked automatically. So the idea is moving from milliseconds to microseconds. AWS Dynamo usually responds with single-digit latency, so 110 milliseconds of latency. But if you want to dial down to the microseconds, you can just enable DAX and add cache nodes. It's charged per cache node. It's just in-memory caching in front of your DynamoDB automatically. So the same that as you would have for many other kinds of, as many people do with Memcached or Redis, but automatically within AWS. So that's DAX. And this is the same in the bottom end of things when you think about performance. And it's always important to understand the why does it behave like this. So RDS is hey Bitworker, what's fix the micro? I would believe you're saying fix the mic, and I hope it's not too bad, and let us know what the issue is. I would be happy to fix this as quick as possible. But what I was saying about the different things is here we can see a very similar theme to the difference between file systems and S3, block storage and object storage. Databases that are indexes that are on the end trees. So database indexes are B trees or other kinds of trees. DynamoDB is a distributed hash map, so it's of course that's more scalable and better efficiency in performance, but it you do have consistency issues, right? And in DynamoDB, consistency, you can define this when you read data from the DynamoDB. So on DynamoDB, on the read operations, you can specify if you want eventually consistent reads. This will give you the first thing it can, as fast as it can, even if it's not entirely consistent, or you can request strongly consistent reads. They cost more. Their eventually consistent reads costs half as strongly consistent, but those you will wait until your cluster is consistent before returning you an answer. So this Dynamo does give you this choice, not when you're provisioning, but when you're reading the data. For some data, you may read them strongly consistent. For some other kinds of data, you can read them eventually consistently as it fits your needs. And this is it for picking your database. So we're done. Understand the CAP theorem and pick your database appropriately. There's many customers running other things such as Cassandra, MongoDB, and a lot of stuff, but if you're new to this, I highly recommend you test RDS, especially with Aurora and MySQL, and DynamoDB would be good candidates for selecting your database solution. And another important aspect of databases is What people used to think about databases recently is being changed dramatically with those new instance types. So if you think that we now have instances with 4 terabytes of RAM, like for many people this is a big data, they call it big data, so but it fits in RAM. So how does this work? How does this change your database? Perhaps you could have 2 Redis nodes of 4 terabytes of memory each and go on and just use memory. I don't know, memory is the new disk for some people. So this is those are decisions that you have to understand. The other things that we were talking about, selecting EC2 instances and database solutions and with the right characteristics of consistency, availability, and network partitioning that makes sense for your app, right? For the network question, so the next thing that you have to select is your network solution, and this is all about ingestion. So usually there's a lot in network solutions. I will not dive so deep on this one, but the thing that you can do to maximize and it's a very low-hanging fruit is use the right service for ingestion. So we have some services that are designed to be the first hit point of network. They're distributed out there to be closer to your user because this network is all about location. And the first I would like to talk about is CloudFront. So we did a lot of this. There's a whole episode dedicated to this, but in the products page, this is pretty clear. Right after the products, we have this global map of infrastructure, and we have 2 kinds of infrastructure. The orange dots, that are the regions, and the blue dots, there are the edge locations. So those edge locations are a different kind of infrastructure to run the services that are closer or that should be closer to the user. For example, if you have users in, I don't know, let me see, for example, in Italy would be a good example. They don't need to go all the way to Frankfurt or to Ireland regions. They can fetch content directly from the edge location in their country. That should be much faster, right? For example, we have 2 in Brazil, Rio and São Paulo, and so on and so forth. So there are many more edge locations than you have regions. So you should target your traffic to that. And one way to do it is for CloudFront. So CloudFront will use this to distribute traffic, and you get to say what we want to do as the origin. You could have an S3 bucket or an EC2 instance or even services in your data center as the origins of content. And when your application is hit, first it will hit the database, then the edge location. If it has the content cached, it will return directly from the edge location. If not, it may go to the origin, fetch the content from the origin and bring it back. This may take a little time, but it will cache this closer to the end user. And this is the whole key to the infrastructure costs, because you can see that you can have the best instance types and the best cost and whatever you want, the best of AWS on a region that has everything, and still distribute traffic throughout this global network of edge locations. And you can even use all regions and all edge locations if you'd like. There are certainly customers at that scale. But for many customers, it doesn't make sense to go cross-region, especially when they're starting. So you can start in just one region and use all the networks of edge locations with CloudFront to distribute content. But the thing is, when you're distributing content, it's a bit different if this is static or dynamic, and you can set most of that in CloudFront. But if you're not having static content, you just want to publish your APIs, API Gateway can automatically use CloudFront. So when you publish your API through API Gateway, it will use the same edge locations, but with more targeted configurations at APIs. Same idea for devices. When you're capturing data from devices, you can use AWS IoT, and it will direct to, in this case, the region, not the AWS IoT lives in the region. It's not an edge service, but it's designed to be the first point of ingestion for IoT devices. You can even use IoT in many regions and use CloudFront or even only Route 53 to distribute among them. And another very important service for ingestion is Kinesis. So let me show you guys a bit of Kinesis. Kinesis is very simple. It will have the same idea of sharding as you have in DynamoDB. But Kinesis streams allow you to adjust throughput. So you get, we have three different Kinesis services: Streams, Firehose, and Analytics. Let's start with streams. So Kinesis streams are just pipes of data. So big pipe to, for example, drink from the fire hose of Twitter or anything that's throwing you a lot of data. You can just say that if you have, for example, one shard can do 1 meg per second or 1,000 records and out 2 megs per second. This is important because you can have your reading paused and resumed later, so it's very important that read is faster than writes. But if 1 meg is not enough and you need 100, you can provision 100 shards, and Kinesis will take care of the distribution of this traffic, just as you would have similarly with Storm and other streaming solutions. But Kinesis is serverless and handles everything for you automatically. But sometimes you are processing this data with apps. Sometimes you just want to throw it on Redshift, on S3, and process later. So we have Firehose that's just that. So if you're on Firehose, you just point your Kinesis stream to deliver data on S3 or Redshift, and you don't have to worry about processing the pipe. It will just store the data for you. And Kinesis Analytics will read your data in real time, see what's going through the pipes, and you can make SQL queries on it. So Kinesis streaming apps, we have a whole episode dedicated to that, so I'm not diving too deep here, just showing you guys how it does look like when you create one. But the whole idea here is that after a while we'll have an application running on our behalf, and we can do SQL queries such as give me the average or the percentiles or any window function within this window of time, a tumbling window, a rolling window, anything that you want to run analytics on a stream of data should be doable on Kinesis streams. So we can go to our SQL editor and start this app that it created for me, this demo. I will add SQL from the templates, and for example, this here is just a count. So it will fetch, I can fetch the count from a symbol or aggregate or run k-means or many algorithms to understand the data that is currently in your plate. So this could be the events that you're receiving from IoT telemetry or analytics on your social data and things like this. So yeah, so so Kinesis is a full solution for all sorts of streaming data applications, and all those without managing a server. So this is pretty attractive. Just to make sure this is clear for everyone, I hope Cleopatra, you're talking about this. If no, let me know. But the idea behind Kinesis is we have Kinesis streams for streaming pipes of data that can go from small pipes to huge pipes and scale as you need to consume data. Firehose if you don't need to process, just store the data and store it on Redshift on S3 and load it later for analytics. And analytics to run SQL queries on the data that's currently on the pipes and run and create things like dashboards or real-time apps. So for example, when someone passes with a device in front of a store that has a promotion, you can alert. Or when it's more than 90 degrees in your thermometers for more than 10 minutes, you may fire an alarm or trigger something like this. So this is easy to make on Kinesis Analytics. So this is streaming solutions. And last but not least, Direct Connect as a network has a pretty important network impact. The idea here is that you can have your dedicated connection to AWS. So instead of going all the way through the internet until you reach an AWS region, you can just have a fiber connection dedicated with consistent network performance from your data centers straight to AWS. So you don't need to go back and forth. And this is pretty important if you have integration. For example, you have a mainframe in your data center. I hope not, but well, there's still some of those around. They are very hard to kill, but they shouldn't prevent your network migration. You could move everything that you can to AWS and use Direct Connect to connect to your own data center directly with predictable network bandwidth, costs, and compatible with all solutions. So, and this is it for the network solution. So we are near the end. We have a few more questions to go, and they are pretty much more focused on the process, so they're not as technical. We're going to be a bit lighter on this end. But the next is, how do you ensure that you continue to have the most appropriate resource type as new things are introduced? And the one thing I would say is keep up to date and always understanding what's coming on and coming along, and there's a lot of ways for that. Do join the meetups, conferences, and industry resources that you have. One that is particularly valuable for me is the technology radars, especially the one from ThoughtWorks. This is hugely helpful. So they classify techniques, tools, languages, and frameworks and platforms into adopt, trial, and or assess. So they are saying that, for example, Python 3 or Ember.jx or Reactive and Redux, or for example in platform Linux security modules or Apache Mesos. So if you're taking a look in this, so for example they classify Lambda as trial, so they have their criterias. Everybody have a different one. They even tell you how to build your own radar, and this may be interesting. And there is this explanation for why they rate it like this. But the specific instance is not as important as the idea of using a radar, yours or someone else's, to keep up to date with technology. This truly helps. And about the meetups, thanks for shouting out, David. MCO65. They are truly important, and here in AWS slash user groups, we have a list of the meetups that we run. We just had Adrian Cockcroft speaking at the Madrid DevOps meetup. We evangelists are frequently there, so if we it's just as nice to hang out with you guys on the meetups as it is here on Twitch, but you get to throw things at me, so and buy me a beer in the next one. I hope I see you guys there. And we do have lots and lots of those. Just pick your continent and you see the list of the meetups that we have. Right now I'm in Madrid, so we do have those everywhere. Do join your closest meetup. And next this is the one side of monitoring performance. The other part is actually monitoring and debugging. So checking where there are the bottlenecks of your app and really make sure you debug those diligently is important. Another tool for that is X-Ray. So X-Ray will allow you to see through your resources and give you overview of where you have the bottlenecks. So it will trace requests across many AWS resources and show you a visualization. Let me show you an example. Let me see if I can get a screenshot. I won't be able to get an app running in time with X-Ray, but here's the idea. Sorry, it's not that real, but you get through all services, and this goes your services and our services. You can see who's a bottleneck, who is running behind, who needs more capacity, who is throwing errors and things like this. So X-Ray is a huge tool to see what's going on in each of the services, and this is internal monitoring, right? This is monitoring your app from the inside and understanding how each component behaves. On Performance 7, how you monitor your resources post-launch and ensure they're performing as expected. You have this active and passive, or internal and external monitoring. And this is internal, how your application is running from inside. But it's also important to look how things are going from the outside. And there are many tools for that. I'm an old Java dude, so I'm used to doing this with JMeter. So you can install and run JMeter from Cask, from Homebrew, as I just did. And once you launch JMeter, we can just create a new test plan. I don't think I can increase the interface here a lot, but I will create a new one and a new test plan and add threads as users. So I will create 10 threads and wait for 3 seconds for them to ramp up and loop 100 times. And you can schedule delay. There's a bit of lots of tricks you can do here to simulate your users. Add requests such as, for example, an HTTP request. Let's fire those requests at our app. So we have that Elastic Beanstalk app running. So let's use that as a target. So this is the URL. And there's a lot you can do and configure. I'm just going a bit quickly on HTTP. This is the default, this is the path, and we should be good. And now that we have a request, I will add a listener and see an aggregate report for this data. So here you can see how many samples, the average, the median, the lines, the percentiles, minimum and max. So if I run this, I should be able to, let's save it before. So those requests are going through, and let's zoom in a little bit. I'm performing nearly 1,000 HTTP requests, and you can see that on average they're taking this time, but on the 90% of my requests are, let's say that good for us is under 200 milliseconds. So 90% of our requests are good, 95% perhaps okay, but we have that 1% that are being problematic, and this is where the bottlenecks lie. So you may, when this happens, look at the X-ray, see where the bottlenecks, fix the bottlenecks, run this again, and so on and so forth until you have your performance measurements done and safe. It's not the loveliest job in the world, but someone is going to do it, and you will learn a lot about your system just by debugging those bottlenecks and getting those numbers the best as you can. So this is surely worth the while. And finally, using trade-offs to improve performance is justifying why you have these weird things. So we talked about many techniques, and I will update this GIST just so this table looks a bit better. And it's all about explaining why did you choose to add caching, for example. Why is DEX there? Or why are you using sharding? Or why does a specific compression and buffering or A/B deployments? So those are all architectural trade-offs. They're harder to explain in other terms and harder to be very precise, but you should go as precise as you can. Not like this is a bit sloppy saying that compression uses time and gains space, but you can say that, for example, well, we choose it to use snappy compression because it does compress our data set to, I don't know, 50%, and we gain a lot of space, so we pay less on S3, even though it takes 20% more to uncompress before analysis, but it's worth it, for example, because it saves us this much money or this much time. And I do recommend you document at least in abstract terms like this, but as precisely as you can, how you trade off to improve performance, and if possible, what exactly the numbers. As everything that with every measurement and the most important part of today's broadcast is this idea. So I hope I show you guys some resources to not talk about performance in so abstract terms. Let us understand and document decisions, especially those selective decisions, why you choose something instead of the other, why you adopted one technique instead of the other. Not in abstract terms, but in as precise and quantitative terms as possible. Some things are hard to get quantitatively, such as documentation quality, but you can get at least a qualitative sense, such as a star rating for that 1 to 5 or things like this. And for every solution that you have, especially compute, storage, database, network, those are the 5 big areas in well-architected, but there is a lot more coming. Someday we are going to see machine learning and other things here, but for most customers, those are the ones that make sense. And I hope you did understand that on compute, we have serverless, containers, and instances. We drove down on the what is an instance and how it behaves. On storage, same thing. Block storage, EFS, and S3 have very different performance characteristics, and we've covered that. But the more we cover, it's always very important to not take this for granted. I could go into the very detailed benchmarks, and I thought about doing so here, but that's not the point. The whole point is showing you guys how you can do your measurement, because only your performance matters on your environment. Mine is nearly irrelevant here. So for this database solution, do review the CAP theorem and how the different databases perform and provide different availability, performance, and consistency guarantees. And the network solutions that we have for ingesting data, they are different for each kind of app, and we covered those two and when they make sense. From IoT to static and APIs. For keeping up to date and monitoring, that's question 6 and 7. Those are two sides of the same coin. How do you make sure that the performance that you thought was correct is still correct? There are only two ways. Keep up with the new stuff, because sometimes you do have huge breakthroughs. For example, Amazon Aurora in databases was huge. So perhaps it's worth taking a look and measuring to see if it makes better for your app's latency and throughput, debugging the bottlenecks, and monitoring on the other side to make sure that it's still valid. So it's with AWS, the idea is that you can change your database configuration and even change your database tier, run your JMeter or whatever you're using for load testing and see how it behaves and document that. And this is how you choose technology based on performance. And not everything can be this precise. For some huge architectural decisions and trade-offs, there's a whole technique that, for example, when you use charging, you change a lot of things at many times. You have some gains, some losses in different areas, and this is how you answer performance 8. It's just how you document those trade-offs. So I hope this gives you guys a good idea of what well-architected performance efficiency is all about. And we've talked a lot about the performance characteristics of the AWS services in general. It was a lot today. Don't worry if you didn't pick it up everything. I hope it was clear enough for everyone to understand. But if it was not, feel free to call me here on Twitch chat. We had a very good chat today. I'm sorry we had some people that was not really contributive, but I really liked the chat about container efficiency and Java startup times. Those are always important, and make sure you understand the difference here is it's not only Java's fault. It's a different thing for designing for servers that are going to run forever and servers that are going to run for seconds. It's totally different design, so keep that in mind and keep in touch. I would love to hear from you guys on Twitter. I will share the links and everything for this session so you can refer back. And see you next time with cost efficiency, where we will learn how to save a lot of money on AWS. Stay tuned.